welcome everyone to 12.6. This is the final section in Chapter 12, Cylinders and Quadric Surfaces. So we're going to be talking about, these are different types of surfaces. This is like an upgrade of planes, right? Planes were our first type of surface. Now we're going to upgrade. We're going to talk a little bit about, well, I guess even before that, spheres, right? We talked about spheres. That's a surface. So we've had planes. Now we're going to talk about cylinders and quadric surfaces. This is going to be like an upgrade here. And so in this video, right, we need to define what we mean by cylinders, because it's probably not what you're thinking. And then we also need to define quadric surfaces, right? So quadric surfaces are kind of like, it looks like quadratic, almost. Quadratic surfaces. And they're certainly closely related, right? They're going to be degree 2 stuff here. And then we're going to go back and think a little bit about some two-dimensional analogies to quadric surfaces. We've actually talked about some quadratic curves probably in your algebra careers. We've talked about like circles and parabolas and things like that. So we're going to go back and make a few of these analogies. That's going to be useful. And then we're going to prepare for battle, right? We're going to look at all these surfaces and we're going to start just thinking about these kind of tougher problems. Okay, so we'll get to that here in a second. Let's get into our definition, right? So, in order to sketch a graph of a surface, which is what we're going to be doing here quite often, it is useful to determine the curves of intersection of the surface with planes parallel to the coordinate plane. So this is a lot of mumbo jumbo. It'll make a lot more sense when I actually do an example here. But these curves are called traces. So these traces parallel to coordinate planes, okay? A cylinder is a special type of surface, as one would guess, that consists of all lines, these are called rulings, that are parallel to a given line, so some specified line, and they pass through a planar curve. Or sometimes we would just call it a plane curve. With an F? No. There we go. A plane curve. Okay, so the claim is that this thing right here is a cylinder. The cylinder Z equals y squared plus 1. And so again, cylinder in Calc 3 means something different than, maybe what you would normally think of in like a geometry class as a cylinder, right? When I say cylinder, people are probably thinking, like this toilet paper roll thing. And so in the Calc 3 cylinder, so the claim is this is a type of cylinder surface in Calc 3. If I was to take, this part right here, and this part back here, right, so that would be a type of cylinder in Calc 3, but there are different types of cylinders. So let me go ahead and I would like to graph this cylinder. And I'm going to pretend like it was on a quiz or an exam or something like this where I don't get to use a computer or a calculator or anything like this. I'd like to be able to graph this thing by hand. So what I'm going to do is when I look at this, I notice that there is no x's, right? There's a z and there's a y and stuff like this. So maybe if I was to start, let's do where I'll graph it, right? So I'll have my x-axis, I'll have my y-axis, and I'll have my z-axis. And so this is where I'll graph it. But I notice again that there are no x's. So I'm interested, if I was to graph along the plane, right? So up here, I'm thinking about traces right now. I'm doing planes that are parallel to the coordinate planes. So z equals 0 is a coordinate plane itself. It's the yz plane, right? If I wanted to graph this thing, well, then this would be down in now just two variables. We have y's and we have z's. So right here, again, this is the yz plane. And if I wanted to sketch this, the claim is I probably know what it looks like now, right? So y squared plus 1, this is going to be a parabola. So if I plugged in y equals 0, I'd get z equals 1. If I plugged in y equals 1, or in fact negative 1, right, I would get z equals 2. And so it's going to be a parabola that opens upward like this. Not the best sketch ever, but it'll do. Okay, so if I was trying to sketch this, and maybe I'll do it in green here for fun, and then I will sketch it over here. So z equals 1, there's the y, and so it would look something like this, right there. And now I'm going to move a little bit over, right? I'm going to do a different plane that's parallel to a coordinate plane, right? So this was x equals 0, an actual coordinate plane. So if I move over and I do x equals 1, right? So x equals 1. Notice, well, I would normally plug in 1 everywhere I see an x, but there aren't any, right? So again, this is kind of a copy of the YZ plane, but it's just been shifted over one. If I wanted to graph the equation z equals y squared plus 1, the claim is that it would look the exact same. It would be a parabola open upward. It would go through z equals 1 here, right? And so it's just been shifted over, right? So if I do x equals 1 over here, and let's see, still I've gone up z1, and then it'll move with y. As y gets bigger, z gets bigger, and as y gets smaller, z still gets bigger, right? So you have the same curve, but now it's been shifted out, x equals 1. Well, what if I did x equals 2, or x equals 3, or x equals 4, or any of these? The claim is the picture would be the same, the same, the same. It would always be the same picture. It's the same as when it was x equals 0, because again, this curve right here, it doesn't have any x's. It doesn't depend on x. So as you change your x value, the curve doesn't change. So as you continue to go out, x equals 2, x equals 3, any of these things, it's going to be the same curve over and over and over again, just shifted out. So you get something like this. And in fact, looking at this, and let's kind of go back and look at these, right, the definition for a cylinder, because the claim is this is a cylinder. You can look at, maybe there's one planar curve here. So this is a planar curve that we bring up. Plane curve, there we are. And we need a ruling, right? Oops, I wanted to use red here. A ruling, so a line that this is parallel to. So this would be one line right here. And so again, cylinders are a surface that consists of all the lines, called rulings, that are parallel to a specific line. Here's one of them right here. And that pass through a planar curve. So if I want them to pass through this purple curve right here, and I make all my rulings, all the things that are parallel, you start to get a surface, right? It looks like a parabola that's just been like pushed and is going in the x direction, and it's leaving behind like shadows or copies of itself. And so this is what the cylinder looks like. And so when we get done, you know, especially in a video where we have technology right in front of us and all that stuff, it's nice to graph and make sure, right? So, okay, I would like to graph y squared plus 1, hit enter, and I'll zoom out a little bit, and you can see it's this parabola thing, but when you go along the x direction, it's just more copies of the parabola. And you can see it generates these rulings, these lines that are parallel to a specified line, and the traces, right? It kind of has these little parabola things. Going over and over again, those are the traces. Okay, so this picture, you know, especially as we, you know, line it up kind of like ours, the claim is it actually looks pretty good, right? For doing it by hand anyway. Okay, but notice it does go on infinitely, right? If I was to zoom out, for instance, it does go on infinitely in all directions, right? It does go on forever. There's no really restrictions on x's or y's here. Okay, I cannot get this to stop spinning. There it goes. Okay, so that is how you can graph a cylinder, right? You're kind of looking at traces. You can think about rulings if you'd like, but really we're kind of isolating the fact that we're missing a variable here. That really helped us out. That was nice. Okay, so that's cylinders. Notice, I guess really quick, this cylinder does not look at all like this one right here, right? This does not look like the typical cylinder that you think of. So they're different when you're talking about a Calc 3 cylinder, right? Okay. Next up, before we move into the three-dimensional stuff, right, let's recall a little bit about the two-dimensional stuff. So I'm bringing up the analogies, right, the stuff, the quadratic stuff, kind of, but for 2 dimensions. So the first friend, right, the one that we all love probably is the parabola. And it has 2 forms, either y equals x squared or x equals y squared. We probably like this one less, but it's okay, right? So these are the kind of the basic forms. The y equals x squared, this parabola looks something like this. It opens up, if this is the x-axis and this is the y-axis. The other one, again, if this is the x-axis and this is the y-axis, it opens to the left, like this. All right, and the final thing, I guess the big thing here that I mentioned is that you only have one squared term, right? So it's either the x is squared or the y is squared, but you only have one of them. Now, moving on, in comparison, right, ellipses. Ellipses, the basic form is actually something like x squared plus y squared equals 1. And this is an equation of a circle, right? So if I was to draw this, we know it would look something like this. But as you add other constants and stuff like this, you know, sometimes you can get things stretched. So maybe you have it stretched in the y direction, right? So this is an ellipse. Or maybe you have it stretched in the x direction. But the big thing is, right, it's circular, but it's kind of been stretched here. So the big thing here is that you have two squared terms, and when you have them on the same side, right, they're both positive. So that's the big thing here about ellipses. Now, the final one, this is everyone's least favorite, hyperbolas, right? So the basic form of a hyperbola is something like x squared minus y squared equals 1, or y squared minus x squared equals 1. So the big thing here is that you have the two squared terms, one is positive, one is negative, right? And so again, these are the basic forms. So this one right here, it looks something like this. Because the x one's positive, the hyperbola opens in the x direction. It looks like this, like this. It almost looks like two parabolas sort of deal, but it opens in the x direction. In this one, because the y one's positive, it opens in the y direction. So something like this and this. So these are the hyperbolas. Again, everyone's least favorite, but the claim is we're going to extend all of this. We're going to need all three of these when we're talking about three-dimensional quadric surfaces. So, okay, here's our definition. A quadric surface is a graph of a second-degree equation, right, with three variables now, x, y, and z. The most general equation is, all right, hold on to your seat. We have ax squared plus by squared plus c z squared, right? So where these are just coefficients here, plus dxy plus xz plus f, let's see, which one am I missing? yz. So those are all the 2-degree stuff, plus gx plus hy plus iz plus a regular old constant j equals 0. Oh my goodness, right? So these are the most general form of quadric surfaces, right? Kind of all of your degree 2 and less stuff. But by translation and rotation, actually, we can actually bring it down to look a little bit more standard. And these are the ones that we would be primarily working with. And this looks something like ax squared plus by squared plus cz squared plus j equals 0, or we'll sometimes be dealing with ax squared plus by squared plus the iz plus, equals 0. So these are kind of the two situations that we're going to be mostly dealing with. So when you have the z squared, right, or you have the z, right? So those are the two big cases. Let's take a look. What do quadric surfaces actually look like? We're going to actually classify these. So I have a nice table here. I have all of the names. I'll give you the general equations and then what these things actually look like. So the first one, ellipsoids. Ellipsoids, the general equation is x squared plus y squared plus z squared equals 1, but then you sometimes scale these things. So you can wiggle the x's, you can wiggle the y's, you can wiggle the z's, right? So you divide by these coefficients, a squared, b squared, c squared. That's why it's the general equation, right? So these are the coefficients that kind of stretch it. And so the claim is this looks like a sphere. Before I do the little mini graph, let's actually go over one more. And I have it graphed for us, right? So I have the x squared over a squared, the y squared over b squared, and the z squared over c squared, all added together equaling 1. And the nice thing about this is, right, we've never done this before, but you can add these slider things. So I've added sliders for a, b, and c so that we can actually change these and see what it looks like. So let me go ahead and change the A's. So I'm going to hit animate here. And you can see as you change the A's, in the X direction, how much this is stretched in or out changes, right? So as A gets bigger here, you can see the ellipsoid kind of expands. Okay, let's go ahead and stop this. And I'll go ahead and reset it to 1. Likewise, in the B direction, if I hit animate here, you can see that now in the Y, right, because it's y squared divided by b squared, as that changes, right, it stretches in the y direction, right? Think about a circle just being stretched out in the y direction. Let me go ahead and stop this. And then you can imagine the C one, that's going to stretch in the Z direction, right? How much up and down the circle is being stretched. Okay, so that's the general one. Let me go ahead and reset these all a second here to 1s. We're going to continue to use this here. Now let's go ahead. So yeah, mini graph, do our best, right? This looks very spherical, but maybe stretched out. So I'm going to stretch it out in the y direction, maybe as best as possible. Something like this. So yeah, this is maybe an ellipsoid here, been stretched out more in the y direction than in the x and the z. So that's sort of what it looks like there. Okay, moving on. Elliptical paraboloid. Elliptical paraboloid, this has the equation, the general equation, x squared plus y squared equals z. And then because it's the general equation, let's sprinkle in some coefficients. We can divide by a squared, we can divide by b squared, we can divide by c here. Okay, so this is what an elliptical paraboloid, the general equation is. What on earth does it look like? Let's go back, take a look. So I need to edit this, right? So I have my x squared, I have my y squared, but now I'm going to make this equal to, and just z divided by c. And there we go. So I hit enter. Ah, cool. So let me go ahead and zoom out a little bit. And so this almost looks like a cone to some extent, like a basket. And so if we move the A's change how we stretch in the X direction. If we move the B's, that changes how you stretch in the Y direction. In and out and in and out. And then of course the C's are going to determine how you stretch in the Z direction. So, ooh, they're negative right now. So it's being stretched down, and then it's going to be stretched up. And stretched higher and higher and higher and higher and higher, right? There you go. So bigger C values means that it's stretched more in the Z direction. If it's negative, right, it's actually being flipped. It's pretty cool. So, again, this kind of looks sort of like a cone sort of deal. We have maybe a couple parabolas here, and then circle, right? So that's kind of what I think about this. Some parabolas and a circle, or, you know, if you want, an ellipse even. So that's kind of nice because it's made out of its name, right? So there's parabolas here. If I look for just a second, you can probably see there's a parabola in the x direction. There's a parabola in the y direction. It's a little bit nasty. Let me reset it here. 1s. Now you can kind of more clearly see the parabola. And then if you were to look at it, oops, 1. If you were to look at it maybe straight up and down, come on, I believe in you, it would look kind of circular or elliptical, right? So these things are actually built out of their names, which is very nice. So if you looked at it straight up and down, it would look like an elliptical, or ellipsoid, or an ellipse, I guess. Likewise, the ellipses, you can see kind of, depending on how you look at it, it's ellipses 3 times. Either if you look at it from the x direction, the y direction, or the z direction, it's all ellipses. So there is actually a system behind these things. Okay, the elliptical comb. X squared, I'm getting ahead of myself, y squared equals z squared. And then of course we divide by these coefficients to make the more general equation. Okay, let's go ahead and see what this looks like. So it's very similar to this, oops, but we have z squared and c squared. Ah, so this is a true cone. It's going in both directions, both up and down, right? So it's made out of some lines here almost. Lines and circles. And so if we animate, again, this is probably my last animation. This is stretching it in the x direction, as it always has been. And as we get big, smaller and smaller a values, it's less and less stretched in that direction. And there we go. Stop. Maybe I'll stop it exactly at 1. That'll be nice. And likewise, changing the b stretches it in the y directions. Changing the c stretches it in the z direction. Okay. So cone, going to look something like this. Has some lines here. And we have kind of some ellipses, right? An elliptical cone. Okay. Moving on. Ooh, hyperboloid of one sheet. Hyperboloid of one sheet has the equations like x squared plus y squared minus z squared, right? There's a minus when we have hyperbolas, so it's kind of no surprise that we get one of these here, is equal to 1. And again, we'll go ahead and sprinkle in some coefficients here to make it the more general case. All right, so x squared plus y squared minus z squared. Let's take a look at what this looks like. Minus z squared is equal to 1. Ah, very cool. So it has kind of, if we're looking at it right now, you can kind of see the hyperbolas, right? They kind of form on the sides here. And okay, so yeah, I won't do the animations again, but you can play with this if you'd like. Again, it stretches it in the x, y, and z direction. But this is cool. It's got like a hole in it. It's like a cone sort of deal, but it's got some space. All right. So looking at this, we have kind of some hyperbolas, even hyperbolas coming out of the page and into the page, and then we have kind of ellipses here to some extent. So that's what a hyperboloid of one sheet looks like. Hyperboloid of two sheets. This we can do like z squared minus x squared minus y squared is equal to 1, and we'll sprinkle in the coefficients. Let me keep this a little bit constant here. I'll use c with the z's, I'll use a's with the x's, and b's with the y's sort of deal. So hyperboloid of two sheets. So, okay, the x's had a minus in front of them, and the y's had a minus in front of them, but the z's were plus. So this one has two minus signs, right? And oh, now it's completely split. Now you see kind of why you have a hyperboloid of one sheet or a hyperboloid of two sheets, right? The two sheets, it has, well, two pieces. And you kind of see, yeah, it's split here, but you still see the hyperbola here and here. So it still has hyperbolas in it, but now it's split and it has two sheets. So a piece up here and a piece down here. So there's one hyperbola. Here's another hyperbola going in and out of the page. And then we have some ellipses here. So that's the hyperboloid of two sheets. And then finally, the hyperbolic paraboloid. Hyperbolic paraboloid, this looks like y squared minus x squared is equal to z. And again, we'll sprinkle in, here's maybe b squared, here's maybe a squared, and here's a c. And the big thing here, we do have to specify c should be greater than 0 in this case. Okay, so let's take one more look here. So I have, let's see, negative x squared, I have the positive y squared, and this time I have it equal to z, but it's z to the first power. Boom. There we go. So this is what it looks like. This is cool. Maybe this one's okay, the picture and everything. It kind of looks like a saddle almost, right? Kind of a saddle that you would maybe put on a horse or something. So actually this is the start of something great. It's called like saddle points and whatnot. You can see that we have, in this direction, we have some parabolas going on, right? We see some parabolas this way. And if you look in this direction, you also see parabolas, but now they're going down, right? Before they were going up, now they're going down. And if you look at it from an up and down kind of viewpoint, you'll see, it looks very hyperbolic, right? You see kind of these hyperbolas in these directions. So that's why it gets its name hyperbolic paraboloids, because it's built out of hyperbolas and parabolas, right? So, okay, these are the ones that are hardest to draw. I'll go ahead and give it a shot, though. So you have parabolas going down, right? Parabolas going down, parabolas going down, and we have parabolas going up in this direction. So parabolas going up, and let's see, we maybe get the hyperbolas going on here. You can kind of see those. And so yeah, I'll kind of shade in, right? This is the top part of the saddle right here. And then the back side of the saddle, you can kind of see maybe a little bit more clearly, right? You kind of see two pieces of the saddle, the front and the back. And this is the Hyperbolic Paraboloid. It's built out of hyperbolas and parabolas, right? And if you go back, you see the hyperboloids built out of hyperbolas, right? And a few ellipses. And the hyperboloid of one sheet, again, built out of hyperbolas and a few ellipses. Okay, in fact, why not? I'm going to go ahead and shade all of these. I like that. I recommend it. All right. So there we go. There are our surfaces, our quadric surfaces. We have the inside of the cone as well. I'll use purple for that up here. How nice. Okay, and that is it for this video. And gives us a nice introduction to these quadric surfaces. The main thing that we want to be able to do, the preparing for battle part of this, is that if I give you an equation, our goal is to be able to figure out what on earth it is, right? So that's going to be the battle, and that's what we're going to be learning about in class to finish up Chapter 12. All right, I'll see you in class. Thanks for watching. See you soon.